Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Chair of Astronomy here at Foothill College, and it's my pleasure to welcome everyone here in the Smithwick Theater and everyone listening to us at home to this special talk in the 19th Annual Silicon Valley Astronomy Lectures. Tonight's talk is about water worlds in our solar system. I'm delighted to report that this series is sponsored by four important organizations in astronomy and astronomy education: the Foothill College Physical Science, Math, and Engineering Division, which has a full astronomy program, NASA's Ames Research Center, the Astronomical Society of the Pacific, and the SETI, the Search for Extraterrestrial Intelligence Institute in Mountain View. And we encourage those of you viewing these programs to check out each of our sponsors. Our speaker tonight is Dr. Kevin Peter Hand, who is a planetary scientist at the Jet Propulsion Laboratories in Pasadena, California, and the director of its Ocean Worlds Lab. His research focuses on the origin, evolution, and distribution of life in the solar system, with an emphasis on Jupiter's moon Europa, which will be a key part of his talk tonight. In fact, he is the pre-project scientist for the Europa landing mission that is now a significant concept in the NASA inventory. He carries out both theoretical and laboratory research on the physics and chemistry of icy moons like Europa. From 2011 to 2016, he served as the Deputy Chief Scientist for Solar System Exploration at JPL and was a member of the National Academy's Committee on Astrobiology and Planetary Sciences. His work has brought him to the dry valleys of Antarctica, the sea ice near the North Pole, the depths of the Earth's oceans, and to the glaciers of Kilimanjaro. Dr. Hand was a scientist on board James Cameron's 2012 dive to the bottom of the Mariana Trench, and he was part of a 2003 IMAX expedition to the Hyperthermal Vents in the Atlantic and Pacific Oceans. We're delighted that he's venturing to the wilds of Los Altos Hills tonight and presenting what I'm really looking forward to, a talk on ocean worlds in the outer solar system. Ladies and gentlemen, Dr. Kevin Peter Hand.
Thank you. It's a real pleasure and delight to be here. Thank you for the invitation, and it's great to be back in this area, as I went to grad school at Stanford and love this part of the state. Tonight I'll be talking about ocean worlds of the outer solar system, and much of our desire to explore these worlds is rooted in the search for life beyond Earth. Now, the search for life beyond Earth covers quite a bit of material. And just to make sure I set your expectations at the right level, tonight I will not be covering UFOs, alien abductions, furry little creatures from distant planets. When I talk about the search for life in ocean worlds, I'm talking about the search for even the tiniest of microbe. Such a discovery would truly revolutionize our understanding of biology and the phenomenon of life. It's a question that has captivated me since I was a young boy, shown here. I really haven't changed much. And I was inspired by wonderful books like this. This book, Our Universe, by National Geographic, showing some sort of floating creature in Jupiter's atmosphere, a big-eared mouse on Mars, and some sort of dinosaur on the surface of a moon of the outer solar system. With images like this, my imagination was captivated at a young age, and I attribute the clear, dark skies of Vermont for getting me into astronomy and capturing my imagination when it comes to the search for life elsewhere. But I like to show this image of Vermont in the background for another reason. And that is that you can see all of the trees that cover the green mountains. And when you think about our home planet, when you think about planet Earth, we find life just about anywhere we find liquid water. North, south, east, west, high, low, hot, cold, just about everywhere you go on our home planet, you find life if there is liquid water. And the story of the search for life beyond Earth is in part the story of our beautiful blue marble reaching out into the solar system and beyond in an effort in part to answer this question of whether or not we are alone. This diagram shows you a line for every robotic spacecraft that has launched from planet Earth. Every spacecraft from every space agency. You see many lines going out to the moon and Venus and Mars and asteroids. But just a few lines extend beyond the asteroid belt. Those are lines that represent spacecraft with names like Pioneer and Voyager and Galileo and Cassini and New Frontiers or New Horizons. We've made many discoveries with those few spacecraft. But in my opinion, one of the most profound and exciting discoveries that we've made using the data from those spacecraft is that we now have good reason to predict that oceans exist beyond our home planet. Oceans of liquid water exist elsewhere in our solar system. And shown here is what I like to call the portrait of at least a few of the ocean worlds of our solar system. At the center, of course, is the Earth with the ocean that we know and love and we need to protect. And around the Earth, I've placed 6 moons of the outer solar system: Europa, Ganymede, and Callisto, 3 moons of Jupiter, Titan and Enceladus, 2 moons of Saturn, and I've even included Triton, a curious moon of Neptune that we think could also have an ocean. These worlds, their surfaces are covered in ice. In the case of Titan, there's an atmosphere above its ice. But beneath their icy shells reside vast, potentially global liquid water oceans. And when it comes to habitability, these ocean worlds of the outer solar system are really changing our framework for what it means for a world to be habitable. In the early days of astronomy and planetary science, there was this concept of a habitable zone, and that habitable zone was largely defined by oceans on the surfaces of planets. In other words, in order to have life, you needed to have liquid water. In order to have liquid water, you needed to have an ocean on the surface. In order to have an ocean on the surface, you needed to be at just the right distance from your parent star, such that you were not too hot or you're not too cold. You had to be at just the right distance. And so in those early days, the habitable zone had this kind of Goldilocks scenario. If you were Venus, you were too close to our sun, you were too hot, you lost any water that you once had. If you were Mars, you were too far away, you were too cold to have a liquid water ocean today. But if you were planet Earth, at just the right Earth-Sun distance, then you could maintain a liquid water ocean in contact with a nice atmosphere, and you could potentially host life. Now, that Goldilocks scenario for planets is much more complicated, but suffice to say that what the ocean worlds of the outer solar system are telling us is that this is an old Goldilocks. There's a new Goldilocks for habitability, and it's a Goldilocks where the energy to maintain and sustain liquid water comes not from your parent star, but instead from the tidal tug and pull that these worlds experience as they go around their giant planets. And there's no better example of this new Goldilocks than the Jovian system and that tidal tug and pull that the moons around Jupiter experience. Shown here is Io, and towards the north of Io, you see a plume. That's a plume from a volcanic eruption. Io is the most volcanically active body in our solar system, and Io is so volcanically active because it's orbiting Jupiter and it's getting tugged and pulled like a ball of taffy, and that mechanical stretching creates heat, and that heat from the interior then causes that liquid water to be maintained under an icy shell. But in this new Goldilocks, Io is kind of like Venus. Io does not have an ocean. Io doesn't, for the most part, have any water. It's got too much activity. And Callisto, though we think it has an ocean, Callisto does not have much tidal energy dissipation occurring, and so its ice shell is very thick and old, and thus if there is an ocean, it's trapped beneath this thick, old ice shell. In the middle, however, we've got Europa and Ganymede. And Europa in particular might occupy this new sweet spot of this new Goldilocks framework, where it's got just the right amount of tidal energy so as to maintain a global liquid water ocean with a relatively thin ice shell, and underneath that liquid water ocean is a rocky seafloor that could potentially harbor what's needed for life. And of course, as I mentioned at the beginning, part of what makes these ocean worlds so compelling is that wherever we've found liquid water on Earth, we've generally found life. The dry valleys of Antarctica, the Rift Valley of Africa, some hot springs in the Rift Valley, deep sea hydrothermal vents. From life in extreme environments to life of extreme lifestyles, all life on Earth requires liquid water. But I like to show this slide for another reason, and that is for all of the diversity of life on Earth, from the most extreme of microbe to the most extreme of rock star, all life on Earth is connected by the same tree of life. All life on Earth runs on the same biochemistry. We all run on DNA, RNA, proteins, and ATP. I'm curious, is there another game in town? Is there a second origin of life out there in our solar system? Is the origin of life easy or hard? Does life arise wherever the conditions are right? Is there a different biochemistry that could underpin some other alien life form? In order to answer those questions, in order to understand a potentially alien biochemistry, we need to go to worlds where life could be alive today. And the ocean worlds, these worlds like Europa and Enceladus and Titan, these are places where liquid water could be today and life could be alive today. Contrast this with our exploration of Mars. I think Mars could well have subsurface life alive today, but for the most part, our exploration of Mars is about the search for past life. It's the search for fossilized life in the rock record. Molecules like DNA and RNA, they don't last long in the rock record, so even if we were to find microbial fossils on Mars, we wouldn't necessarily be able to say that it ran on DNA, or that it had some other biochemistry, or that it was even a separate tree of life, distinct from our tree of life that we have here on Earth. So these ocean worlds really offer the opportunity to potentially find life that's alive today, where we can study its biochemistry and answer that question of whether or not the origin of life is easy or hard, are we alone, and what does this life possibly look like? Thanks. How do we think we know these oceans exist? Could these oceans beyond Earth harbor life? And what can life on Earth teach us about potentially habitable environments beyond Earth? And shown at the right are the three keystones for life that I like to use in setting the framework for how to think about whether or not these ocean worlds could be habitable and possibly even inhabited. We'll start with water. How do we think we know these worlds actually have these liquid water oceans? I'll use Enceladus and Europa as two examples, and what I'll show you for those worlds broadly applies to the other ocean worlds of the outer solar system. So first and foremost, it's important to appreciate that much of what we know comes from the robotic missions that we send out into the solar system. Shown here on the left is the Cassini spacecraft in the spacecraft assembly facility at JPL. You can see a human there for scale. In the upper right is the Galileo spacecraft. And this was a pretty unique shot. Typically, you don't get a shot of a spacecraft actually in space. But Galileo was sent up on the space shuttle, and so astronauts were actually able to capture a picture of it before its engine fired to take it on its journey, actually inward in the solar system, eventually pinballing out to Jupiter. And of course, we wouldn't be able to receive the signal from these spacecraft if we didn't have the ear on the ground, the Deep Space Network. And so it's important to include that in our framework for how we actually get the data. And those zeros and ones, of course, come back and yield stunning images like this. Shown here, of course, is Saturn with its rings and many of the moons of Saturn. One of those moons, Enceladus, is about 500 kilometers in diameter. It's a small world. Here are the Great Lakes for reference. It's a small but very, very curious world. When the Voyager spacecraft first sent back initial images of Enceladus, the images were not a very high resolution, but even with those images, scientists could see that the icy surface of Enceladus was pockmarked by craters in the north, but to the south, there were very, very few craters. This image is from the Cassini spacecraft, and you can see that pattern again. To the north, many craters. To the south, very few craters. Craters are like footprints in the snow to a planetary scientist. If there are many footprints, the snow is old. If there are no footprints, it's fresh snow. So to the south, the question became, how could this region be so young? What's happening? Well, upon closer inspection, it was revealed that there were at least 4 stripes crossing the south polar terrain of Enceladus. These fractures are now known as the tiger stripes. And with the brilliant engineering of the engineers down at JPL who were able to configure the Cassini spacecraft in just the right spot, scientists were able to look at these fractures from an angle where they could see something astonishing occurring. Okay, clearly I need to prompt you. Ooh, there we go. I know you all just saw a picture of a black hole, but plumes on Enceladus really deserve an ooh and ah. What you're looking at here are jets of water erupting out into space from those fractures in the south polar terrain of Enceladus. These jets contain not only water, but also carbon dioxide, methane, some small carbon molecules, some salts, and even some silica, some tiny little grains that might be from a seafloor within Enceladus. Now, early on, when the jets were first observed, everybody was excited about the prospect that these jets might be connected to an ocean below. But we proceeded with caution because we've seen jets elsewhere in the solar system. Comets, of course, have jets. Comets have these beautiful jets of water that also have carbon dioxide and organics in them. And so when the Cassini spacecraft dove through these jets and was actually able to taste the material in these jets, it discovered the water, the organics, the methane, the carbon dioxide, but really the definitive nail in the coffin connecting these jets to a liquid water ocean below was the discovery of salts. Comets do not have salts. In order to have salts like sodium chloride or magnesium chloride or potassium chloride, you need to have liquid water interacting with silicates, liquid water interacting with rocks. And so for me and many of my colleagues, when the Cassini spacecraft revealed salts in the plumes of Enceladus, that was the real connection to an ocean below. And so our current conception for what Enceladus looks like is shown here. Again, it's about 500 kilometers in diameter. It's got this icy shell that's maybe 10 to as much as 50 kilometers in thickness. In the south, it's fractured, and those fractures connect to the ocean. The ocean itself is perhaps many tens of kilometers in thickness, and beneath that is an undifferentiated mantle. There's not a dense iron core at the center of Enceladus. There's basically this conglomeration of rocky material. This is, for the most part, the end of our knowledge of Enceladus for the time being. We still have a lot of data to parse through from the Cassini spacecraft, but as most of you appreciate, the Cassini spacecraft went into Saturn's atmosphere not too long ago, and so we are no longer receiving new data about Enceladus. We need new missions to get out there. Shown here is a mosaic of one of the highest resolution collection of images that we have of Enceladus' surface. Each pixel here is about 6 meters per pixel, or roughly the size of this stage. And what you're looking at is water ice and perhaps some other materials on there. And each of those fractures possibly connects to one larger fracture that could eventually get to the ocean below. So if you or a daring robot were able to dive through one of those fractures, you might actually be able to get down and swim in that alien ocean. So with Enceladus, the case for the liquid water is actually leaping out at us. The Cassini spacecraft was able to taste the water of Enceladus' ocean. When it comes to Europa, the science is a bit more subtle. It's beautiful physics, and I'll step you through it in 3 easy pieces. To put Europa to scale, here's Europa. It's about the size of our moon, but of course Europa orbits Jupiter, which is some 318 times as massive as the Earth. We're all familiar with the tidal tug and pull between the Earth and our moon. We've all seen the tides rise and fall in our shores. At Europa, some of the predictions indicate that the rise and fall of the surface of Europa might be as much as 30 meters, or nearly 100 feet, with each time that Europa goes around Jupiter. So how do we think we know that Europa actually has this liquid water ocean? Well, as I mentioned, I like to break the discovery into 3 easy pieces. The first piece of the puzzle is to find a rainbow connection. This is not about Kermit the Frog. It's when I talk about a rainbow connection, I'm using the term rainbow as an easy term for spectroscopy. Much of what I do in my lab, much of what many of my colleagues do when we use spacecraft and telescopes, we do spectroscopy to try and figure out what the surface composition of a world is. Spectroscopy is a fancy word for studying rainbows. If you take a rainbow, turn it on its side, and look at the intensity as a function of color, as a function of wavelength, you have a spectrum. And by looking at that spectrum, you can figure out the composition of whatever the light's passing through or reflecting off. In the case of a rainbow on Earth, you can figure out things about the composition of our atmosphere, the composition of the water droplets, the composition of our sun. In the case of Europa, you can figure out that the surface of Europa is actually made of water ice. And that's exactly what the Russian scientist Vasily Moreau did many years ago. Moreau and Gerhard Kuiper, both sort of founding figures in planetary science, turned their telescopes to the Jovian system and collected some of the first spectra ever of the moons of Jupiter. And what you're looking at here is a rainbow turned on its side. It's an infrared rainbow. Down at the bottom there, that's wavelength in microns. So we go from 1 micron on up to about 2.5 microns. And that sort of stepwise feature that you see there, with absorptions at 1.5 and 2 microns, that is highly characteristic or diagnostic of water ice. And so with the first piece of the puzzle, using ground-based telescopes, astronomers were able to figure out that Europa's surface is covered in water ice. Some 350 years after Galileo discovered Europa, it goes from a point of light to a big ice ball. But we haven't gotten to an ocean yet. For that, we need another step. And here I like to make the analogy to babysitting a spacecraft. In this analogy, Galileo is the baby, and the Deep Space Network is the babysitter. And by carefully babysitting a spacecraft, you can collect information on the spacecraft's trajectory. And you can actually monitor at the centimeter to millimeter per second scale how the spacecraft speeds up and slows down, redshift and blue shift of the transmitted signal, how the spacecraft speeds up and slows down as it flies by a world. And that slight shift in the blue and red shift of the transmission coming from a spacecraft can then be used to figure out the gravity structure of a world. And from the gravity structure, you can then figure out the interior mass distribution of that world. Now, there's a lot of physics and detail on this. It's actually sort of physics 101. I won't go into it tonight, though I was told that there's a whiteboard back here somewhere that I could use if needed. But I'll skip through this. And the upshot of that beautiful physics is that by carefully babysitting the Galileo spacecraft, scientists on the Galileo mission were able to reconstruct the mass distribution of material within Europa. And they determined that Europa has an iron-sulfur core, a dense core. Over that is a less dense, but still somewhat dense, rocky silicate mantle, similar to what we have on Earth. And then what the data revealed is that there had to be a low-density outer layer. And that low-density outer layer needed to be about 100 to 200 kilometers in thickness. And the density of that material needed to be roughly 1 gram per cubic centimeter. And a material that fits that density profile quite well is water and water ice. So we go from knowing that Europa's got ice on its surface to now knowing that Europa has water in either liquid or solid form for its upper 100 to 200 kilometers. The gravity data is not sufficient in resolution to distinguish between the density of ice and the density of liquid water. So we're not yet at an ocean, but at least now we know that there's a thick water layer in some form. To get to the actual conclusion that an ocean exists, we need the final piece of the puzzle. And this is where I like to make an analogy to adhering to airport security. I've shown you all these beautiful pictures from spacecraft missions. I apologize that this picture is blurry. This was at JFK Airport, and I was trying not to get arrested, so this was sort of a photograph on the move. But what do I mean by adhering to airport security? Well, when you walk through one of those doorways at airport security, you're walking through a magnetic field. You're actually walking through a time-varying magnetic field. The magnetic field is pulsing up and down. And if you have a conductor in your pocket as you're going through that time-varying magnetic field, Maxwell and Faraday taught us that that time-varying magnetic field will create electric currents, which will create induced magnetic fields in that conductor. And then within that little doorway are sensors that detect the induced magnetic field in whatever metal you've got in your pockets. And the alarm goes off because this little piece of metal created an induced magnetic field. When the Galileo spacecraft flew by Europa, the alarm went off. The Galileo spacecraft had on board a magnetometer, a fancy compass, and it essentially acted like one of the sensors in the airport security. Meanwhile, Jupiter itself, with its large time-varying magnetic field, is akin to that doorway that you're walking through. And so when Europa passes through Jupiter's magnetic field, or rather Jupiter's magnetic field sweeps past Europa, there is a time-varying magnetic field that can create electric currents and an induced magnetic field. So when the Galileo spacecraft detected an induced field, when the alarm went off, the question became, there needs to be a conducting layer within Europa. Well, based on the spectroscopy and the gravity data, maybe that conducting layer was that iron core. We know that iron is quite conductive. Doesn't that answer the mail on creating an induced field? You run the models, and it turns out it doesn't. The core is too small, too far away. What about that rocky mantle? It turns out that rocks are not that conductive. What about just ice? It turns out that ice is not that conductive. But what fits the Galileo magnetometer data beautifully is a salty liquid water ocean beneath a relatively thin ice shell. The salty ocean of Europa set off the alarm. That is ultimately how we think we know that Europa has got this induced this ocean beneath its ice shell. And again, it's beautiful physics. Goes back to Faraday and Maxwell, Physics 101. There it is, but here is the result. We now think that Europa's got an ice shell that's maybe a few to as much as 20 kilometers in thickness. Beneath that is an ocean of roughly 100 kilometers in depth. And beneath that is a rocky seafloor. Sadly, the Galileo spacecraft plummeted into Jupiter back in the early 2000s, and we're left with just a few tantalizing close-up images of Europa's surface. Here again, the resolution is about 6 meters per pixel. Everything that you see in white is water ice. The grays and black here, this is a grayscale image. So the grays and black here are perhaps salts from the ocean below, perhaps material from that ocean, perhaps little squid fossils. I can dream. Here, for reference, that cliff, that ice cliff with all that dark talus, is perhaps a few hundred yards or a few hundred meters in height. So these three easy pieces, the spectroscopy, the gravity data, the magnetometer, that actually applies to, in part, Ganymede and Callisto, and to some extent Titan. And so that's how we think we have an understanding that the liquid water oceans exist. What about the elements that are needed for life? How do we think we know that these worlds might have that keystone for habitability satisfied? Well, what do we even mean when we say the elements for life? What elements does life need? Well, when you look at the periodic table, it turns out that life uses a smattering of roughly 54 elements from the periodic table. Shown in green are the ones that are essential for all life, and those are pretty light elements. Shown in red and some of the darker colors are some of the heavier elements, the metals that life needs. And interestingly, when it comes to the elements that life needs to build life, there's another kind of Goldilocks situation. It turns out that despite evidence to the contrary, Earth is actually a bad place for life. I know, you're all looking around and you see life, and clearly it works. But when we think about the elemental inventory of what's needed for life, Earth has, to some extent, more carbon and more water than it really should. The early solar system baked out a bunch of our inner planets. Think about Mercury, think about Venus, think about Mars, think about the asteroid belt. Earth also was, for the most part, baked out. And we think that perhaps some of the water that we now have was accumulated later from comets coming in and delivering at least some of that water. Meanwhile, the outer solar system was a lot colder. And so ices of water and other materials like methane and sulfide and sulfur dioxide, and a lot of the molecules that contain the lighter elements of life, they froze out as ices in the outer solar system. And so when Europa and Enceladus and these other moons formed, they actually had good initial materials to provide some of those lighter elements that are needed for life. This is a plot showing you where ices form, and I won't go into detail on this, but simply put, if you look at the bottom there, the outer solar system, where you're further from the sun, it's colder. And so materials like not only water, but methane and ammonia, et cetera, can freeze out. And so Europa, Enceladus, and Titan had a lot of those materials, whereas the inner solar system, where you're hotter and closer to the sun, a lot of those materials were basically baked out. So when it comes to the light elements, being further out in the solar system was actually a good thing. What about the heavy elements? Well, you can think about density as a good proxy for whether or not these moons have enough rocks to provide you with the metals that are needed. And so when we think about these moons like Enceladus and Titan and Europa and Triton, we can look at how they fall on a plot like this, where keep in mind that water and ice has a density of about 1,000 kilograms per cubic meter. And so if you're at about Mimas there, then you're basically a moon of all water, a big ice ball, and you don't have much rock to give you the heavier elements. Meanwhile, if you're too far up, you're pretty dry. You're like Io and the moon. And so if you go too far up, you've got too much rock, too little ice. If you go too far down, too much ice and too little rock. But if you're in between there, you might be at that sweet spot where you have not just the light elements, but also the heavy elements that life needs. Meanwhile, if you're too big, like perhaps Titan, Ganymede, and Callisto, you might actually have a seafloor of ice because the pressure gets so intense at the bottom of those oceans that you form ices of a higher ice phase. And I won't get into detail on that, but it's still an open question as to what those seafloors might actually look like. So how do we think we know that Europa and Enceladus in particular have these elements that are needed for life? Well, here we go back to spectroscopy. We can look at Europa's surface, both with images and also with spectrometers, and we can see things like the discoloration shown here. This image is of Europa's surface. It's about 200 kilometers across. These little dimples are about tens of kilometers in diameter. The fractures that you see, those are fractures that we think may connect to the ocean below. And the reddish material is, I think, and many of my colleagues think, salt from the ocean below. And the salts, as I mentioned before, are a good indication that you've got liquid water cycling with a rocky seafloor. Here's another image showing a chaos region on Europa where we think there might actually be an upwelling of heat that then causes ice to convect and breach the surface and fracture kind of a brittle layer into all sorts of things that look like icebergs, but we know they cannot be icebergs because the ice is far too cold. The surface of Europa is about 100 Kelvin, or roughly minus 280 degrees Fahrenheit. So on Europa, this is our current model. We think it's got that rocky seafloor where the ocean water is leaching through the seafloor, providing salts to the ocean, and then fractures and eruptions potentially bring that material to the surface. Meanwhile, at Enceladus, if you recall that image I showed you earlier, there's not really much discoloration on Enceladus' surface. Spectroscopically, when we look at Enceladus' surface, we see little else other than water, and that's still a bit of a puzzle. But the Cassini spacecraft actually flew through and tasted those plumes, and on the right is a mass spectrum, some data revealing sodium coming out of the plume of Enceladus. And so we think at Enceladus, the ocean is cycling with that seafloor, and through the fractures, some of those salts are being delivered up to the plumes, and that's what Cassini actually was able to sample. So that's it for the elements. What about energy? Here's where things start to get a little bit tricky. The final keystone, energy. What does it really mean to say that life needs energy? Well, when we think about life on Earth and we think about energy, we often just look up in the sky and we see that big glowing orb that we know and love and call the sun. And when we think about the energy for life, we think in the context of photosynthesis, and photosynthesis serving as the base of the food chain. But on a world like Europa, or a world like Enceladus for that matter, photosynthesis is probably not a viable niche. Sunlight is most likely not going to make it through an ice shell that's kilometers in thickness. Photosynthesis is not going to power the base of a food chain within these ice-covered ocean worlds. So what other options are there? What kind of chemistries could potentially help power life within these ocean worlds? This is where it comes back to our home planet. And now I'm going to transition into some stories and some exploration of planet Earth, where by studying life in extreme environments on planet Earth, we can better understand how various ecosystems on Earth survive without the power of our sun. They survive by doing chemosynthesis instead of photosynthesis. They use the chemistry available in their environment to do the business of life. So the first stop is Alaska. The north slope of Alaska is dotted by some 10,000 lakes in the permafrost. And during the summer, as shown on the left there, these lakes are open to the atmosphere. They get sunlight, and everything is nice and happy. You can see grass of the tundra doing just fine. But then as winter comes, those lakes freeze over. And some of those lakes are bubbling out methane. And we know that it's methane because we can actually puncture into some of these holes and light it on fire. And the person on the right there is a brilliant engineer who I think I see sitting in the audience, John Lichty, who used to be at JPL, now is at Toyota. And so I don't have time tonight to go into detail about the microbes that are producing the methane and the microbes that are eating the methane. But suffice to say, during winter, there's no sunlight up there, but the microbes are still churning away. They are producing some of the methane that we see. Much of it we think is actually is coming from deeper in the geologic base of this region. But by studying this methane and the microbial ecosystems up there, we can potentially learn about what might serve as a biosignature for methane coming from a world like Enceladus or Europa. And to that end, we've developed a robotic vehicle that can help us study these ecosystems when we're not there. Because of course, we're fragile human beings. We don't want to stay up there all winter long. But robots don't mind that. So I'd like to share with you a little video that National Geographic made highlighting some of this work. Let's see if I can get the volume up.
The rover that our team has developed is an early precursor of something that we may someday fly to Europa. The buoyant rover for under-ice exploration is designed to float on the underside of the ice and rove as if the underside of the ice is the ground. These ecosystems up in Alaska, these lakes that freeze over every year and freeze down, they're just one example of life in an extreme environment that can help guide us in assessing whether or not a world like Europa could harbor life. We cut a hole in the ice, put the rover underneath the ice, and then left it out there to rove around. And we went back to the nice warm Quonset hut, and our team was even able to hand over control to engineers down in JPL. And so we think this truly was the first time ever that an underwater, under ice, untethered vehicle has been operated through satellite link. Our work has this wonderful marriage of advancing our understanding of what's happening on our own planet while simultaneously feeding forward into our exploration of potentially habitable worlds beyond Earth.
Now, as beautiful as that environment is, it's relatively shallow. The ocean of Europa is very deep. The pressure within Europa's ocean is going to be much higher than what those microbes making and chewing on methane would experience up in those permafrost lakes of Alaska. And so to get to pressures and conditions that are a little more comparable to Europa, we need to go out in our own ocean. And to do that, we need a boat. A big old boat. And many years ago, I was invited to be part of an expedition to explore ecosystems at the base of our ocean, these hydrothermal vent ecosystems. These are systems where our planet is cracking apart and producing new oceanic crust, kind of like a conveyor belt of rocks. And so here we're diving down into the ocean, going to the mid-Atlantic ridge. And just like a seam on a baseball, along the mid-Atlantic ridge are these well, not like on a baseball, there are not hot springs on a baseball, but along the seam of the mid-Atlantic ridge are these hot springs that are erupting out a host of chemicals that life in these environments can feed on. This is what they look like in person. This is what's called a black smoker because it's churning out these minerals that look like black smoke. Really, it's pyrite and other metal particles that are coming out of the chimneys. But here in this deep ecosystem, we're cut off from sunlight, and the microbes are having a feast. The microbes are what you see in that sort of white and yellowish mat around the chimneys. And then they serve as the base of the food chain. They're doing chemosynthesis, chewing away at those chemicals, and then the crabs, the shrimp, the other creatures that you see, they form the base of the food, or they form the higher organisms in the food chain. Now, this is a very active hydrothermal vent system in our ocean. As we've continued to explore Earth's ocean, we've discovered that there's a wide variety of geologic settings for hydrothermal vents. Shown here is a vent system that's called Lost City. It's called Lost City because it's got these beautiful carbonate chimneys, these beautiful white rock chimneys that rise off of the seafloor. And Lost City is not powered by the energy of new rock being made. Rather, it's being powered by an exothermic reaction, kind of like a hand warmer on a cold day, where when ocean water mixes with that deep rock, it creates heat and it creates compounds like hydrogen and methane that microbes can then feed on. And there's actually some compelling evidence that some of the chemistry that we see in Enceladus's plumes is similar to some of the chemistry that we see at Lost City. And along with the microbes at Lost City, we also see beautiful creatures like this. I was the first to see this creature on our dive at Lost City, and not being a marine biologist, I just called it a space bagel. This creature is about almost 6 feet in diameter, an absolutely beautiful ctenophore. But these hydrothermal vents, this one is at about 1 kilometer depth, and the one that I showed you before is about 3.5 kilometers depth. That's deep, and the pressure is definitely high there. And 1 kilometer down in our ocean is equivalent to just about the pressure that we think would be at the base of Enceladus's ocean. But it's nowhere quite near the pressure that would be at the base of Europa's ocean. Europa's larger, so the gravity is stronger, and the pressure is higher as you go down into Europa's ocean. To get to true Europa-like pressures in our ocean, there's really only one place you can go, and that's the Mariana Trench. And in 2012, we had an expedition out to the Challenger Deep. It was the first time that a human submersible had returned to the Challenger Deep, which is a depth of about 11 kilometers, roughly 7 miles. It was the first time that a human had returned to that depth in our ocean since 1960. It was led by James Cameron, funded by him and National Geographic and Rolex, an absolutely incredible expedition. I did not make a dive here. I made dives at the other sites. So when people ask me, what did the Mariana Trench look like, I say, well, it looked like this. But trust me, that is the Mariana Trench, and if you drop a stone there, it goes for 7 miles down. The human submersible, the Deep Sea Challenger craft, was absolutely astonishing. It was assembled and tested in a matter of months, which for a planetary scientist and astrobiologist is incredibly fast. And so this, as I'm sure you all appreciate, the expedition was successful. James Cameron got into the very, very tiny sphere here, and he's a pretty large, tall guy, and so for him to stay all crunched up for the better part of 7+ hours, it was quite a feat in and of itself. He came back to the surface alive. The engineers all took a big, deep breath. But along with the Deep Sea Challenger vehicle, we also had 2 robotic vehicles, landers for the deep ocean. These are vehicles that are about the size of a telephone booth, engineered by Kevin Hardy, shown there on the left. And the beauty of these more simple systems is that we could just leave them on the bottom of the ocean for a long time. And we could monitor baited traps and other instruments that we left down in the deep, dark abyss. Humans, of course, you gotta give them air and make sure they stay alive. But these vehicles could survive for quite some time. And so sure enough, when we dropped one in the Challenger Deep and looked and waited to see what came out of the darkness, we saw this. What you're looking at is the end of a robotic arm that is released from that telephone booth-sized vehicle, and it crashed down on the sediments of the Challenger Deep. And above the little color bar there is a net, and in that net is a fish head. And that fish head, after a few minutes, after tens of minutes, after a couple of hours, attracted the attention of creatures that we call amphipods. And after a few hours, it went from just a few amphipods to hundreds and possibly thousands of them. You can see a cloud of them in the background there. An absolutely astonishing observation. Here in the deepest, darkest, most extreme environment in our ocean, we find not just microbial life, but we find complex organisms. Beautiful, complex organisms. And when I say beautiful, I mean truly beautiful. Just look at this thing. Now, whenever I show this picture, there's always a child in the audience who wants to know, what did it taste like? Sure enough, one of the engineers tasted one after I was finished dissecting it. Soon after he tasted it and digested it, he went to the side of the boat. To put it politely, he then returned that little creature from the ocean from which it came. It did not taste good. That little yellow packet is sulfur. But as amazing as that observation was, as astonishing and as beautiful as that ecosystem was to see, those amphipods, it raised a big scientific question. We brought that fish head down there. We baited the trap. What are all those creatures eating when we're not around? What's the base of the food chain? How is that ecosystem working? That's really what my colleagues and I wanted to know, both to better understand the depths of our own ocean and also to be able to extend that understanding to worlds like Europa, Enceladus, Titan, and the other ocean worlds. Well, we think we got the answer to that question on a subsequent dive with a lander. We dropped it in a region called the Sirena Deep of the Mariana Trench, just a little bit further up the side of the trench. And what you're seeing here is a drop of that robotic arm, again with that color bar, again with the trap on top. And it crashed into the side of a cliff. We serendipitously landed on the side of a cliff. And after the sediments settled, and thankfully some of the sediments actually went into a sampling bottle shown there. After the sediments settled, we were able to see this. Okay, now I don't have a little prompt here that says ooh and ah, but if there are any geologists in the audience, you should be oohing and awing, because what you're looking at is outcrop, actual hard rocks at a depth never before seen in our own ocean. Previous dives in the Mariana Trench, the Challenger Deep, had gone down to that 11 kilometers depth, and all you see down there are accumulated sediments. We got lucky and landed on a cliff just above the deepest region, and lo and behold, we were able to see this rocky outcrop. And what we think we're seeing in that outcrop is a bit of serpentinization, that same process that drives the geochemistry of the Lost City hydrothermal vent site. And when we took a closer look in at the rocks, this is what we saw. And this is where the biologist should be oohing and awing. What you see coming off of these rocks are filaments of what we think are microbial mats. These are microbes that are doing chemosynthesis. These are microbes that are feeding off the gently percolating gases that are coming up through those rocks. Gases perhaps like hydrogen sulfide and hydrogen and methane, some of the materials that we sampled and were able to detect. And so here, in the deepest, darkest, most extreme environment in our own ocean, we see that there is energy to power life. And so we think that this gives us some hope that that final keystone, if you have a deep, rocky seafloor, you may be able to provide not just the water and the elements needed to allow life to exist and to build life, you might also have the geochemical energy needed to power life. So where are we going? What are we doing? What's the next step in our exploration? This diagram shows you a bit of a pathway for our exploration of Europa's ocean. In the upper right there, you see a spacecraft that's now called Clipper. The Europa Clipper mission is moving forward. NASA is committed to that mission, and it will launch hopefully in the early 2020s, ideally in the 2023 timeframe. And Europa Clipper will orbit Jupiter, and it'll make some 45 flybys of Europa. It does not land, it does not have an in situ component that will go to the surface, but it will do incredible mapping with cameras, with spectrometers, with ice-penetrating radar, and all sorts of instruments to give us a global perspective on how Europa actually works. And some of that data will also hopefully feed forward to a mission with which I'm heavily involved, which is the next step in that progression, landing on Europa's surface. And now I'd like to share with you an animation that's based on CAD models and technical data of our latest incarnation of the Europa lander mission concept. I've been working on this, and our team has been working on this for several years now. What you're seeing is a spacecraft in the belly of a carrier spacecraft. The carrier spacecraft would have solar panels to help power it. The spacecraft, the lander itself, would be encased in a biobarrier. The spacecraft would be baked out here on Earth and then enclosed in an envelope to make sure that no little bugs on Earth can hitchhike. Out of that biobarrier would come the lander, and the mothership, the carrier spacecraft, would go on past Europa and orbit Jupiter. This spacecraft, you're looking at the bottom of it right now, so you're looking at its belly pan and some of the legs. It then heads towards Europa, where it has to do a deorbit burn. And all of the thruster firings that you're going to see next, these are all actually engineering validated thruster firings. This is not just some artist making these firings. After the solid rocket burn happens, that motor's jettisoned, and then we come down to Europa's surface, and we use a small version of the sky crane that was used to land the Curiosity lander. The cricket-like legs or grasshopper-like legs will allow us to land on a surface that perhaps has undulations and terrain that is hard to accommodate at the scale of the lander. This vehicle will not rove or move, it's a stationary lander. Once it's down on the surface, the antenna, which has cameras on the back, will collect a panoramic image that will be used both to appreciate the beauty of the surface, but it'll also help us figure out where to sample. After we figured that out, the robotic arm will be deployed. And this arm, we've been doing some development and testing down at JPL on variations on the cutting and sampling modalities for getting into minus 280 degree Fahrenheit ice that perhaps has lots of salts in it. And so we've got a bi-blade saw sampler, which gets us down beneath the surface, and then a scoop with a rasp would go and collect a small handful of material. That would then be brought back to the vault of the lander. And inside the vault would be instruments like a gas chromatograph, mass spectrometer, perhaps some sort of infrared spectrometer, and hopefully even a microscope. And the main goal of this mission would be to seek out signs of life in the surface material of Europa, to see whether or not it makes sense to go even further into the ocean below to potentially answer that question of whether or not we are alone. Now that mission I've already spent over a decade working on, and in the best case scenario, it lands on Europa in the early to mid 2030s. This business is not for the faint of heart. One of my first mentors, Dave Morrison, is actually in the audience, and he appreciates the long history of passing the baton and how this stuff is not for the faint of heart. And so NASA is not yet committed to this mission. There are many science priorities that have to compete for resources in terms of what we study. But it is my hope that moving forward, we could actually get this mission to the launch pad in the mid to late 2020s so that we can land in the early 2030s and early to mid 2030s. And after that, I see some young people in the audience, is my ultimate dream of dream missions. This is not a NASA animation, this is a Hollywood animation made by James Cameron and his team. It's actually quite accurate from an engineering standpoint. In this mission, we're now following on the results of that first lander, and we're trying to get through the ice to the ocean below. And in order to do that, you need a melt probe. That melt probe would have a heat source on the front end that would allow it to melt or possibly drill through the ice. And behind it would be a tether and possibly some acoustic transponders that would allow data to be relayed up through the ice where it could then be sent back to Earth. Once in the ocean, the nose cone would come off and out would pop an autonomous underwater vehicle. And this would need to have a lot of autonomy because we're not going to joystick this from JPL. Once there, it goes down to the bottom of the ocean, and in my dream of dreams, we find some hydrothermal vents. And at least in this Hollywood vision, we then make contact with incredible alien jellyfish, and we change our understanding of life in the universe. So with that, I'll conclude with what is arguably my all-time favorite image from the history of solar system exploration. It's an image carved by the hand of Galileo, an image carved over 400 years ago. At the center is Jupiter, and around Jupiter are 4 little points of light that Galileo saw when he first turned his telescope to the night sky in 1610. Nobody had done that before, and so when Galileo first looked at Jupiter and saw those little points of light, he thought they were stars. He thought they were stars that he wasn't able to see, that were in the background. And being no fool, Galileo's paycheck, his research was being funded by the Medici family. So he called them the stars of Medici to keep the checks coming. But night after night, he charted those little points of light, and he saw that they moved. He saw that they revolved around Jupiter. That, of course, was heresy, and that got him in trouble with the Inquisition. I won't go into that. But with Galileo's observations, he put the final nail in the coffin of Aristotelian cosmology, and he helped ignite the Copernican revolution. We went from a worldview where the Earth is at the center and everything revolves around the Earth to one in which the Earth goes around the sun. Our sun is a star. The stars that we see in the night sky could well be suns to their own planets. And in the decades that would follow Galileo, we would come to appreciate that the laws of physics apply not just here on Earth, but also to worlds and wonders beyond Earth. And with the advent of spectroscopy and better telescopes and better tools, we would come to appreciate that the principles of chemistry also work beyond Earth. And then with the advent of the space age and a robotic exploration of worlds like our moon and Mercury and Venus, et cetera, we would come to appreciate that the principles of geology work beyond Earth. But when it comes to that fourth fundamental science, physics, chemistry, geology, biology, when it comes to biology, we have yet to make that leap. When it comes to the science of us, the phenomenon of life, we have yet to make that leap. We don't yet know whether or not biology works beyond Earth. We don't know whether or not the origin of life is easy or hard. We don't know whether or not life arises wherever the conditions are right, or if life on Earth is some sort of biological singularity. And part of what excites me about the time in which we live is that for all of the centuries and millennia that we have been staring up at the night sky, wondering whether or not we're alone, for the first time in history, we can actually do these great experiments. We can design the robotic vehicles, develop the tools, and go out and explore worlds like Europa, Enceladus, and Titan, and potentially answer this age-old question, potentially bringing our universe to life. Thank you very much. Let's see, I'm left-handed, so I'm going to start with the left.
Great talk. First of all, thank you very much. Recently, Dawn has completed a pretty substantial survey of Ceres, which I believe they've reported they think there might be a liquid ocean there as well. And I was wondering if you might be turning your sights there since it's a bit closer and maybe more accessible.
Yeah, Ceres is an absolutely beautiful world, which once upon a time was a planet, but as many of you appreciate, it's now classified as an asteroid in the asteroid belt. And so Ceres, it's unclear whether or not it has any liquid water in its interior today, but based on the available data, I certainly think that Ceres in the past had liquid water. And so there's sort of a class of objects that my colleagues and I are starting to call relic ocean worlds. Worlds that had oceans in the past, may still have some pockets, may still have an ocean, but we don't really have a closed case yet for Ceres. But certainly, as you mentioned, it's closer, and it's an incredibly exciting world to explore for many different reasons. So I hope we do get out to Ceres.
Thanks.
Thank you again for the talk. I had two quick questions. One is general about probes in general. A lot of them don't seem to have very powerful microscopes on them, and you mentioned that the probe you were talking about was optional, and I wanted to know why. And second of all, and finally, is why is it a lander and not a rover? How much more difficult is it to roam, and what are the challenges?
Yeah, two great questions. With respect to the microscope, atomic force microscopes have flown on a couple of occasions. The Rosetta mission had one, but as you say, I think our instrument portfolio within NASA and our mission framework needs more microscopes for Mars, for Europa, for Enceladus, et cetera. And just recently, NASA initiated the Instrument Concepts for Europa Exploration -2 round of instrument development, and a microscope was funded in that. I hope that maybe more microscopes could be funded for additional development, because if we see the chemical signatures of life, I sure hope we can actually look at it and look for morphologic or shape indicators too. And then the roving, too risky. We don't know what the surface of Europa looks like at the centimeter to tens of centimeter scale, and we don't really know what how that upper surface, the regolith, will behave. So do we need crawling legs? Do we need wheels? I think we could build a rover now that might be able to rove, but it would have to have every bell and whistle on it to make that possible. And typically when we land on the surface of a world, the first landers are stationary and do the recon into surface properties to help us figure out how to then implement mobility.
Why not just drop a rover on, and if it can't roll, just call it a lander?
Money! so we actually have a couple of rover-esque things, cryobot athlete things at JPL that have wheels on the ends of some of those legs that you saw in the animation for the Europa lander. I would love nothing more than to have something that moves, but at the end of the day, one of our key mantras is better is the enemy of good enough. And part of the rationale there is with complexity comes increase in cost and comes both cost and schedule risk. And a surefire way to have a mission never hit the launch pad is to do the most complex mission. Okay, back over to the left.
I'm lucky to know Bill Borucki personally of Kepler, and he says that you don't need to land. There are plumes of materials over there, I think at Europa, or one of those moons, Europa, I think he said, that they're coming from below the ice, so you could just orbit, catch them, and even return, return to the Earth. Do you plan to do that, or is it not a good idea?
No, I think that's a great idea, and I've been a part of some teams that have proposed a mission to go out to Enceladus to fly through the plumes, and I think we should get that done. That's a great example of a relatively low-cost mission that NASA could do with very high science value, flying through the plumes, collecting material, looking for, doing what Cassini did, flying through the plumes of Enceladus, but doing it with a much more capable instrument payload. So hopefully we'll do that in the decades to come also. Thanks. A friend.
With your lander, you said you'll scoop material from the surface and then look for signatures of life, and I was wondering what those signatures would be.
Yeah, so it's a great question, and if we had another hour, I could go through everyone. But at the highest level, one of the things that's most important is that you have a biosignature framework, a set of measurements for signs of life that is complementary and redundant. In other words, if one measurement type fails, you have another measurement type that can sort of pick up the slack. But then if one measurement succeeds, you also have some complementarity there that, if you find a sign of life with one type of measurement, like looking for complex organics with a mass spectrometer, that's going to be incredibly compelling. But if that's all you have, you're not going to conclude that you've found life. In order to do that, you need to, say, look at it with a microscope so that you can associate the complex organics that you see with a structure that looks cell-like. And then with those organics, you might actually look for chirality to see whether or not there's any preferential handedness of, say, amino acids or sugars that's in that material. Then you might also look at isotopic fractionation. And you also definitely want to look at the context, making sure that you got material that you have good reason to predict came from the ocean below. So that's just one example of chemical measurements, including the complexity of the organics itself, looking for things like amino acids, the chirality, the isotopic fractionation, looking for minerals that might also be associated with life, things that we typically think of biominerals, and then the structures, the cell-like structures that can complement that. So I encourage folks who want to learn more about that to Google Europa Lander Science Definition Team report. We had a team of 21 scientists who dissected exactly this question and generated a 260-page document on what types of measurements we would prioritize to make on the surface of a world like Europa. Let's see, so let's go back over to the left.
Yeah, maybe I misheard something, but when you were talking about the relative pressures, I think envisioning for one of your probes, it would go under, I would say, the water surface, but obviously some of these are not water. But if I heard correctly, you implied that the larger bodies, like the larger moons, would have greater pressure than the smaller moons, where in my layman's mind, I'm thinking, wouldn't the depth of the liquid be the primary determiner of how much the pressure was? What am I missing?
Yeah. So you're talking about that chart that I showed with Ganymede and Callisto and them being too big and having icy seafloors?
Yeah.
Yeah, so what's interesting there is that if you get down to several hundred kilometers in, say, Ganymede, you get to a pressure where you form things like ice 3 and I believe 6, these different crystalline structures of ice. All the ice that we see on the surface of these worlds is ice 1, the type of ice that we have in our freezers at home. But when you get to really high pressures, water forms a solid that is called things like ice 1, ice 6, et cetera. And that form of ice is denser than liquid water, so it sinks. Does that make sense?
Yeah, it makes sense, but I'm missing the distinction between whether the depth of the body of water is more important with respect to pressure, or is it the diameter of the body that's more important?
It's both, yeah. So in a world like Ganymede, you would have ice 1 making the ice shell itself. Then you'd have the liquid water, and that would stay liquid as deep as it can go until it hits that pressure point where all of the sun water says, we can't be in liquid phase anymore. Let's bind into a new crystalline structure that's one of these higher phases of ice.
Okay, is there a lot of difference because of the gravity variation?
Well, the pressure is a function of how much mass there is, which is also where the radius of the moon serves as sort of a rough proxy for the total mass of those moons, which is why Ganymede, Callisto, and Titan, such large moons, and they're also very massive moons, have larger gravity, and so in their depths, you get these higher pressure phases of ice.
Higher pressure at the same...
Sure. It's a...
Give everybody a chance, so let's move on.
Sure.
All right. So I have a couple of questions. The first one has to do with those fractures on Enceladus. So I was wondering if there are any hypotheses about how they formed, so like why there's 4, and also why they're parallel.
Yeah, it's a great question, and a fair number of papers have been published on this, and there's no real good consensus, in my opinion, on your second question, which is why they formed in that curious parallel structure. But what's causing the fractures in the first place, we think, is the tidal tug and pull. And there's lots of debate also about why just the South Pole, why not fractures everywhere? There we think that the tidal pumping of Enceladus may have, just by a curious feedback loop, created a hotter, more tidally active geologic region at the South Pole that acts kind of like a hydrothermal blowtorch that's creating a thinner ice shell in that region, which then fractures easier. And there's even a few publications that say that the fractures open and close as Enceladus orbits Saturn.
Okay. And then the other question, are there plans for sending some sort of DNA sequencing technology up?
Yeah, it's a great question. And in theory, I would love to send something like a DNA sequencer to these worlds. The problem with that, and this comes back to the question from my friend earlier, the problem with the DNA sequencer is that you're biasing your detection type to what we know, which is DNA-based life. And so if there was some life form on Europa that did not have DNA or didn't have the same sequences, that DNA sequencer would be like, nothing here. Meanwhile, there might be some other biochemistry happening.
Because I thought I'd heard about, I think it's the nanopore sequencer,
Yep.
right? That has like the pore, and it like sequences based off of the change in the size of that hole,
Yep.
right? So I thought that one of the coolest things about that was people were saying that you could possibly sequence molecule or like DNA bases that weren't just ACTG. You could use it for...
Well, and so those pore-based systems, I think, are a good example of you can actually make them more generic so that they could characterize large molecules for you. The problem, of course, is that the biotech industry, they're incentivized to make these DNA sequencers for health and medical reasons. There's not that much money to be had in making an Oxford nanopore that's going to go to Europa. But I certainly hope those companies are excited and want to be a part of the mission.
Okay, thank you.
Thanks for the questions.
Yeah. In your 3 easy pieces, the second piece was gravity, and you showed 3 layers on the moon. Could you say more about how you can use gravity and possibly other technologies to determine the internal structure of the moon?
Yeah, so with gravity, what you ultimately tease out is the moment of inertia. And that's what that sort of whiteboard slide that I clicked through somewhat quickly shows you. And once you've got the moment of inertia, you can start to figure out the interior structure. Now, I've played around with those equations, and I can create solutions that have 5 layers of material, or 10 layers, or there's not a uniqueness yet given the available data. But given the data, a 3-layer basic model was justifiable and ultimately publishable. And so, at the end of the day, but if you had a spacecraft in orbit around Europa, then you could do incredibly sensitive gravity mapping, watching exactly the little perturbations. You might even see the spacecraft wiggle from a seamount, a volcano within Europa's ocean. With the flybys that Europa Clipper will make, there's a chance we could actually tease that out of the data. It's making a lot of flybys. I hope we can do that. But Clipper also has some other techniques, magnetometry, to do the interior sounding. It's got an ice-penetrating radar that will tell us about the possible intersection of the ice layer with the ocean below and any pockets within the ice itself. I really want to have a seismometer on the lander so that we can listen to Europa quakes. As the ice cracks and creaks, we can hear that and get information about Europa's ice shell and possibly even collect echoes of those quakes off of Europa's seafloor to figure out the exact depth of the ocean. So those are a few of the techniques.
So the three-layer model is plausible, but we're not certain about it, clearly.
That's right. It's the simplest viable model at this point. Back over here.
I'm switching.
I would love to see any young students in the audience. We've got some students here. Excellent. So please get up and ask some questions.
Yeah, I'm switching from the depth of the ocean to the depth of the actual ice layer. Are there any predictions, prior to Clipper going there, what the minimum distance of that would be? Because I assume that's where you'd want to go.
Yeah, there's a huge debate in the community about how thick Europa's ice shell actually is. You want to see scientists, planetary scientists, really get into something and argue. Europa's ice shell is a great topic. So I'm on the thin side of the fence. I think that Europa's ice shell might be a few kilometers to maybe 10 kilometers in thickness. Meanwhile, there's some really good arguments to be made for the ice shell being 10 or 20 or possibly even 30 kilometers in thickness. At this point, we have no more available data, but with the Hubble Space Telescope, we do have some pretty compelling evidence that there are plumes jetting out of Europa's ice shell. We did not see plumes with the Galileo spacecraft, and that may have simply been that the Galileo spacecraft was limited in its observations of Europa. So the evidence from Hubble is pretty exciting, and that may be some places where the ice shell is thinner, or perhaps at least connecting to some ponds of liquid water in the ice shell itself.
Thank you. I was young once, by the way.
Okay, sounds good. Let's come back over here.
First of all, I'd like to say that was a fantastic talk.
Thank you so much for coming.
And you kind of mentioned this before in a previous question, but you mentioned some of the elephants like carbon, phosphorus, sulfur, and some of the others that are crucial for life here, for bodies on Earth and life forms on Earth. But is it necessarily appropriate to assume that maybe moons like Enceladus or Europa will have similar requirements for rudiments of life like nucleotides or like the genetic sequences?
Yeah, it's a great question and one that I love to ponder for exactly the reason that you mention it. Carl Sagan used to say that he was a carbon chauvinist, in part based on just the affinity that carbon has for playing well with other elements in the periodic table. And certainly at standard sort of planetary temperatures and pressures, life with water as the solvent and carbon as the key building block for life makes a lot of sense. And when it comes to designing missions and doing experiments on other worlds, we have to kind of partition our investigations into hypothesis-driven science and discovery-driven science. I can stand here today and generate a scientifically sound hypothesis that carbon and liquid water-based life could potentially have arisen within these ocean worlds. I can't point to anything on Earth and tell you in good conscience that I have a really viable hypothesis that silicon-based life, ammonia chewing life, it could work on these worlds. That falls into a category that we call sort of discovery-driven science. And I hope that when we do eventually land on Europa, we have an instrument payload sufficient to see both life as we know it and weird life, life that might be based on some different complement of elements in chemistry.
And I had one more question.
I'm sorry. We have 5 people waiting, and we need to get done. So I'm going to just say the 5 people who are standing now
is it done?
each get 1 question.
Okay.
And then we-
Thank you so much for your question.
We also have a person that was sitting, so we need 6.
Okay, over here.
Okay, thanks for the great talk. Now, there's a mention of salt maybe on Europa. What is the ocean believed to in saltiness compared with the Earth's ocean?
Yeah, that's a great question. I wish I actually did much of my PhD on exactly that question. And using the magnetometer data to kind of constrain what the conductivity is and what the salinity could then be. I think it's in the range of the salinity of Earth's ocean, possibly a few times saltier. But really, we're just going to have to wait for the Clipper mission and then the lander mission to get out there. I do think the primary salt is sodium chloride, similar to the main salt we find in our ocean.
Hello.
Next question over here.
Hello. Sorry. You sort of went in this direction. I was thinking that you mentioned the possibility of life that was not based on DNA. And I was, wondering if you had any other hypotheses about what that might be, and also maybe rather than water, maybe liquid methane would be a possible solvent.
Yeah, it's another great question. And one of the things that's great about Titan as a world that is in our own solar system backyard is that we kind of get a 2-for-1 when it comes to astrobiology. We think that Titan has a liquid water ocean beneath its ice crust, but then on Titan's icy crust are these lakes and seas of liquid methane and ethane. So we can investigate those lakes and seas to explore and see whether or not methane solvent-based life has found a way. And so I can't really see a truly viable biochemistry that connects the dots, but we have a place like Titan where we can do both hypothesis testing and discovery-driven science to see whether or not a truly weird type of life exists out there in the Saturnian system. Back over here.
Well, this is more speculative, but if life were discovered, I'm just curious, and you were forced to gamble, would you gamble on life being originated one place in the solar system, spread by meteorites, for instance, or would it be independent? And if you had some colleagues, would they argue with you, or I'm just curious if we had 10 of you up here and answered the question, what kind of answers would people give? Just speculatively, obviously.
Well, let's take it a given that scientists would argue. That's just a universal truth. But I think we would at least be able to partition ourselves into a couple of camps where, let's say we went to Mars and even found life that's alive today, and it turns out that it is DNA-based. I think the Occam's razor is that DNA-based life on Mars was at some point in the past connected to life on Earth. Earth and Mars were transferring material, as you indicated, in the early solar system. And so what Mars had, Earth got. What Earth got, it's like the flu in the solar system. And so I think DNA-based life on Mars would probably have some connection to life on Earth. And even if it didn't, it would be hard to prove otherwise. If we went out to Europa and found DNA-based life, I would say, boy, it's actually pretty hard to cross-contaminate Europa with Earth-based DNA life. And planetary scientist Brett Gladman up at University of British Columbia did a brilliant simulation where he ejected something like 6 million particles from the Earth and let them travel throughout the solar system. And I believe it was only something in the range of a dozen actually made it to Europa. And of course, once they get on Europa, they're impacting at somewhere in the range of 11 kilometers per second. So they're basically destroyed on the surface, and everything is lost there. So I think it's actually hard to have that kind of cross-contamination of these ocean worlds of the outer solar system. So DNA-based life there, to me, would be indicative of a second origin where you see that there's a convergent biochemical push towards DNA, which I think is very profound.
Great, thank you.
Next.
Thank you for a wonderful lecture. My question is regarding the Europa lander mission. When your lander lands and punches through a hole through the thick ice sheet, aren't we encouraging water plumes gushing out of it?
With the melt probe going down through, absolutely. You would have to be careful of what happens behind the probe, and do you keep it open? Do you let material freeze? What's going to happen is Europa has the tidal interactions, which creates new fractures. There are many, many unsolved problems in this great engineering challenge. And one of the ways that we're trying to kind of develop the baby steps towards a melt probe on Europa is by doing a better job of figuring out how to do it on Earth. And just like the buoyant rover that I showed you, this has got the great win-win of increasing our capabilities for exploring extreme environments on Earth so that we can understand the home planet, while simultaneously kind of kicking the tires and innovating in a way that we could have small, robust, capable systems that someday we could put on top of a rocket and get out there to worlds like Europa.
And let's suppose...
No, one per question.
Sorry, thank you for your question. And then over here.
Thanks for that enlightening talk. I enjoyed it very much. So coming back to the Mars question, is there actual interest in trying to find life on Mars, given that it has an icy pole or ice caps out there?
Yeah, in the Mars community, there is an effort and a lot of excitement about going to places like the icy polar caps, and even to some ice deposits that you see in some of the higher latitude craters. And goodness, I would love just to have a little rover that rolls up to the side of that ice deposit, that ice field, and looks for microbes that are maybe feasting away on some methane that's seeping out of the Martian permafrost and surviving on trickles of liquid water that don't last long but come out of the glacier and allow those microbes to make a living.
Thank you.
Is that it?
I think that's it. Let's thank Dr. Hayne again.
Thank you so much.